When cold fluid enters a heated pipe and exits hot, energy is added to the flow. This energy moves inward from the pipe wall, represented by heat transfer rate, Q dot. Regardless of the heating method, total energy gained must satisfy a foundational balance, the product of mass flow rate, specific heat, and temperature rise. However, the way that heat enters the fluid depends entirely on the condition of the pipe wall. In practice, the surface will be maintained at either a constant temperature or a constant heat flux. These conditions are mutually exclusive. You cannot have both at once. Imagine an electric resistance heater wrapped around the pipe. It adds a steady amount of heat per unit area. This constant input forces the wall temperature to climb as the fluid warms. By contrast, a pipe in boiling steam is locked at a fixed temperature. As the fluid warms, the temperature gap shrinks, reducing the heat transfer rate.
Identifying which in these two scenarios is at play is the mandatory first step. This diagnosis dictates the mathematical framework you must use to solve for the final heat transfer. Under a constant heat flux, the energy added per square meter of pipe remains uniform along the entire length of the flow. Mapping this on a graph shows a steady, predictable rise. Since the heat input is constant, both the mean fluid temperature and the surface temperature increase at a fixed rate, forming two parallel diagonal lines. Because these lines are perfectly straight, the temperature change is linear. This allows you to use standard arithmetic averages to find your values. Now we look at the constant surface temperature path, where a boiling water bath might lock the pipe wall at exactly 100 degrees Celsius. Here, the graph changes. While the wall temperature stays flat, the fluid temperature climbs rapidly at first and then levels off. It follows a curve that approaches the wall temperature without ever quite reaching it. The vertical distance between these lines represents the driving force for heat transfer. As the fluid warms, this distance shrinks, causing the rate of heat transfer to drop off as the fluid moves toward the exit. Because the fluid temperature follows this curve rather than a straight line, an arithmetic average of the inlet and exit temperatures will overstate the actual heat transfer. The calculation requires a more precise way to account for the nonlinear change. This is where we use the log mean temperature difference. The formula introduces a natural log component to the denominator. This natural log function accounts for the continuous exponential decay we see in the temperature difference between the fluid and the wall. To see this in practice, pause the video here. Use this exponential formula and the parameters to find the fluid's exit temperature. As we substitute the values, look at the behavior of the exponential term. The negative exponent mathematically forces the temperature gap to narrow as the surface area and distance increase. When a pipe wall is at a fixed temperature, relying on this exponential relationship is the only way to determine the fluid's true exit temperature. Once the exponential calculation provides the exit temperature, the difficult part of the analysis is complete. You can now take that exit temperature and plug it directly back into our foundational energy balance to solve for the total heat transfer. Every internal convection problem begins with this universal energy balance. The math then branches. Constant heat flux yields linear changes, while constant surface temperature creates an exponential curve, requiring the log mean temperature difference. Mastering internal forced convection comes down to correctly diagnosing that boundary condition at the start and applying the specific math it demands.